Understanding Streamflow is very easy if you know what you're looking for. Let's get into the key concepts.
The first major idea necessary to understand streamflow is velocity. Sir Isaac Newton defined velocity as a change in position divided by the elapsed time. An easy to understand example is a runner. We have a watch we can use to time the runner, and we know how far the runner will go. Thus, we can calculate the velocity. In this case, the runner went 100 meters and took 10 seconds. Thus, she had an average velocity of 10 meters per second.
Set.
They get away first time. Powell has got a very good start, so did Dix alongside him, but here comes Usain Bolt. Usain Bolt streaking away from the field. It's going to be gold for Jamaica. That is superb. It's a new world record. He has blown them all away. Usain Bolt.
Streams are not as simple. They don't always take a total linear path, and it's not a single entity like a runner. Instead, we have to treat the stream as a collection of water molecules, all moving at different velocities depending on where they are in the stream. The ones at the very bottom and the outsides of the stream will move much slower because they are rubbing up against the solid surface of the ground. The molecules at the top are rubbing up against the air molecules, interacting with them as the water rushes past, also slowing them down, though not as much as the water on the bottom and the sides of the stream. Transforming the velocity profile into something we can use, like a function, is simple enough. If we are using data points, simply switch the data so that the depth is on the x-axis and the velocity is on the y-axis. If we're using a best fit function, we can solve for v as a function of depth. To change depth to height from bottom, just subtract the total depth from the depth at any given point and take the absolute value. The mean value theorem is a way of using calculus to find the average of a complex function. In our case, we are looking for the average velocity. To use the mean value theorem, first find the area under the transformed curve. Then divide this value by the depth of the stream. A Riemann sum is a method of approximating an integral that uses the height of a given function at an evenly distributed interval to find the area under a curve by breaking it down into simple rectangular shapes. It's slightly prone to error, but usually is close enough to get the job done. The United States Geological Survey has measured thousands and thousands of streams. This represents a sufficiently large sample size with which to make a generalization. The data shows that more often than not, the average velocity will occur at 60% of the depth of a stream. This means we don't even have to bother with the mean value theorem, in most cases, to get a good idea of how fast the water is moving. Furthermore, USGS research has shown that average velocity is usually between 80 to 85% of the surface velocity of the stream. This makes it significantly easier to measure, as it means we no longer need to worry about suspending our measurement devices at depth. That covers velocity. Now on to the other important determiner of flow, area. A cross-section is the area of an item looking across its face. In the case of a stream, imagine a plane going from edge to edge and all the way to the bottom. If we froze the water in time and looked at it from the path of the water, we would see a roughly semicircular shape. This shape represents the cross-sectional area. To measure the cross-sectional area, first run a tape measure across the surface of the stream perpendicular to the direction of the flow. Then calculate a regular interval you wish to use. An even number of interval works best. For a small stream, divide by 5 or 7. This ensures a point will be in the center of the stream, where the velocity is the fastest. Then take a yardstick and measure the depth at each interval. This will give you a depth profile. Calculate the area by treating each regular interval as a trapezoid, with a height at each end equal to the corresponding depth at that point. Then sum all of the trapezoidal areas you calculated and you have the cross-sectional area. Now that we have both the average velocity and the cross-sectional area, we can calculate the volumetric flow rate, typically denoted by Q or V dot. Volumetric flow rate is a measurement of how much water is flowing, usually in cubic feet or cubic meters per second. To get this value, multiply the average velocity by the cross-sectional area. Make sure your units are consistent. For example, only combine feet and feet, not feet and inches. Notice that the V for volume has a slash through it, like an upside down A. This is distinguish it from the V used for velocity, which here is marked with a bar to denote that it is an average. The dot above it denotes that the volume is flowing and not static, as compared to the reference plane of the cross-sectional area.
Fortunately, you can approximate the velocity of a stream with the help of a friend using a few items you should have laying around your house.